I would say that we may start. There is no voter. I don't see voter online, so I assume that he's not available. I don't get any message from him. So you, Stephanie, and you, Edith, you will manage this session. It's the longer session, apart for the sustainathon of this edition, because we arrive at 7:30 with 8 speeches. So I would just give my welcome to all the attendants and to all the speakers. And I leave the floor to Stephanie and Edith, not necessarily in this order, for the presentation of the session, the speakers, and a brief introduction of what we will see in these 2 hours and a half. Floor to you, Stephanie or Edith.
Okay, I'll go ahead and start. Welcome everybody to our really exciting PFAS remediation session. I'd like to welcome you today. I'm Stephanie Fiorenza with ASTM's Committee E50. Edith, would you introduce yourself?
Hello, everyone. I am Edith Martinez Guerra. I'm a research environmental engineer with the U.S. Army Engineering Research and Development Center, which is a lab which is part of the Army Corps of Engineers. And most of my experience is in water and wastewater treatment and bioenergy. Welcome.
Welcome. We also have another co-chair, Wouter Gewurz. I probably butchered his last name, possibly even his first name. He's with Nicole and also Arcadis. By the way, I'm also a principal scientist with Arcadis. And he was going to be introducing some of the early speakers, I believe, but I'll just go ahead and handle that right now. Our first presentation.
No, I think I'm the first one.
You're doing the first one? Go. Okay, great.
The first one. Yeah. Sorry. Yeah, our first speaker is Dr. Jeffrey Lewis. He has a PhD in hydrogeology and is a docent at Gothenburg University as ECT2's general manager in Sweden. Jeff is bringing his patented ion exchange regeneration technology to the Swedish market, technology which has been proven in multiple full-scale PFAS remediation projects in Australia and in the US. His research is focused on characterization and remediation of PFAS in groundwater, and he'll be talking to us about the early PFOA breakthrough in GAC pilot system. So welcome, Jeffrey or Dr. Lewis. You are muted.
And now I should be good. All right.
There you go.
Is everything working? Does this all look right?
Yes, sir.
Yeah. All right. And just to confirm, I've got 20 minutes, right?
Yes.
Okay, awesome. All right, well, thank you very much for this opportunity. I'm going to start my stopwatch here. This is going to be something of an unusual conference presentation. We've been running a number of pilots, around the world. ECT2 is, as you got from the beginning, it's emerging compounds treatment technologies, and we're best known for our ion exchange regeneration system, but we're by no means bound to that. We're interested in providing the client with the most cost-effective solution. So, in some cases that's GAC, in some cases that's IX, in some cases that's foam fractionation. We have quite a bit of experience in all of them. So when we meet a new client, we're looking for, how are we going to approach their problem? How are we going to tailor our solution to their needs? And so what I'm going to be presenting here is talking about a result that took us by surprise. And honestly, I don't think that we have an adequate explanation of what is going on here. And I would be more than welcome to hear anybody out there who's listening, who has, some thoughts about what may be happening here. It's as simple as that. So yeah, so let's get going here. there we go. So a little bit of background. The client is a drinking water provider in the town of Gävle, Sweden. Now this is already right off the start, it's kind of interesting because the influent concentrations are not that terribly high. The PFAS levels vary between 20 and 53. It's, you know, it varies over time. And here in Sweden, we have a limit, although it's a recommendation really, to stay under 19 nanograms per liter for the sum of the 11 compounds that you see on the right of the screen. So the client is forward thinking, and they understand that, you know, those of you in Europe are well aware of the Drinking Water Directive and the EFSA document that was brought out late last year. It's inevitable that the levels, the permissible levels in PFAS are going to be reduced, probably by quite a bit. We don't know by how much, but it's going to go down. And they simply wanted to be proactive and to get a handle on how are we going to be treating this water? What will we need to do? The most cost-effective way to get this PFAS optimally under detection level. So what we did is that we ran a side-by-side pilot using activated carbon on one side and ion exchange resin on the other. And you know, in so doing, we get very nice breakthrough curves on both sides and figure out the economics of what system is going to be optimal. So here's how it's, you know, none of this is particularly strange. We've been running these pilots around the world. We've done dozens of them. We've used, you know, exactly the same methodology here as we have in the States and in Australia and with our pilots in Germany. So both the IX and the GAC system is running in 2 columns in a lead lag configuration. So there's 4 columns total, 2 IX, 2 GAC. Identical, as I mentioned, to other pilots. This is an important point that we'll get back to later. And the GAC and the IX lines are also identical. So we sample weekly at 5 different points, the influent, after the first column, and then after the second column. So a little bit of the drilling deeper here on the technical level. Contact times for the GAC is 5 minutes per column. So 2 columns is a 10-minute contact time total. IX much lower, 2 minutes per column, so 2 and 4 minutes. Flow rate, therefore, is quite a bit different. So you've got 880 milliliters per minute on the IX side and less than half that on the GAC side. The bed height here, we're looking at the GAC. So this bed volume right here, that's 91 centimeters. The IX is on the other side, so we can't see it, but that's okay. It looks exactly the same, except it has ion exchange stuff inside instead of the GAC. So total bed volume, it's just under 2 liters. All right. So all of that is good. It's also important, and we'll get back to this again later. This is great water. You know, prior to the PFAS being detected, this was a really great source of raw water for the drinking water plant at Gävle. It's coming from an esker. So the quality of the water is great. Since they've been running this well for years, they have 196 different parameters that they've been measured, you know, over a period of multiple years. Here's just you know, a few of them that are typically of interest for remediation. You know, the chlorides, the TOCs. You know, that this can have impacts when it comes to adsorptive media. So just to give you an idea of what the water looks like, you know, I just selected some of the average concentrations that we're seeing here. Okay, now the influent PFAS concentrations, as I mentioned earlier, they're quite low. What's interesting here is that it's almost all PFOA. 80 to 90% Depends, again, a little bit on when we measure, but 80 to 90% of it is PFOA. There is some PFHXA, PFHXS, very little PFOS, and the shorter chains, the PFBS, PFBA, they're just above detection limit. So, you know, single digits or lower nanograms per liter. So what we ended up doing is 3 separate experiments, and they're all essentially run the same way. So the first trial we ran between October and January of last year, and here, as I mentioned earlier, for the GAC, and we'll focus on that, 5 and 10 minute empty bed contact time. The next one, trial 2, is an exact duplication of phase 1, except we took out the GAC and we put in some new GAC, okay? It's exactly the same GAC. We just did everything exactly the same, repeated, looking at repeatability if we're gonna get the same results. And then on the third one, again, experimental conditions are identical with the exception that we used a different kind of GAC. And I'm not going to get into the kinds of GAC that were being used here. The purpose of this is not to point out, that, these ones are not working. That's not what I'm getting at here. We have very confusing and strange results, and I want to focus on, what is happening on more of a physical level than like pointing out what GACs may be the cause of this. So here's some results, okay? And, from the first trial, we saw these results and we assumed that something must be going wrong. All right, so what we're seeing here is that the light blue, that's the lead GAC column. So the water that has already come through the lead GAC column, and we see breakthrough within 8 days. And it's exclusively PFOA. None of the other compounds that are present, it's only PFOA, and that's the same all the way through. So we kept running it, and we started seeing breakthrough in the lag column as well. Meanwhile, the IX is working exactly the way we wanted it to. The source water for both sides, it's just a split. It's exactly the same water, exactly the same source, okay? Everything is the same. And we're seeing these weird results. So what we assumed was that we must have done something wrong. We're not expecting to see, breakthrough in the GAC that quickly. It just is not reasonable. So we redid the experiment. We did exactly the same thing, took the GAC out, put some new GAC in, restarted, and it looked like this, almost identical. So now we start trying to problem solve and trying to think. We still are not accepting these results as being representative of what is, what should be happening. Our experience tells us we have a pretty good grasp of the kind of GACs that we're using. We're expecting to see the breakthrough on the GAC much later, certainly not within the first week. That's just not what we expected to see at all. So now we started to wonder, maybe it's a bad batch of GAC. Maybe it for whatever reason, maybe it's not performing the way that it should be. So we went to another manufacturer, used a different kind of GAC that we'd used in the past, used that in the experiment, put that in, and we got this. So again, the IX, we kept the IX in after trial 2 because we still hadn't seen any breakthrough curves on the IX, and one of the purposes of this was to achieve the breakthrough curves for the IX for the purposes of being able to calculate. So we just kept going with the IX. The IX kept running. This is for trial 2, and then just kept running it out into 100,000 bed volumes. Meanwhile, for the GAC, we start seeing breakthrough, again within a week. All of this is really weird. We don't really understand it. Like we're trying to eliminate the potential sources of error here. What could be happening? So it comes down to this. Why are we seeing this early PFOA breakthrough in the GAC? And as I mentioned, we've talked to a lot of people. We've shared this data transparently with both GAC companies and asked for their feedback, some thoughts on what could be going wrong. And here's a short list, well, somewhat short list, of some ideas of what could be happening here. Now, number one, naturally, you can go to the equipment and think the apparatus, what could be going wrong? What could be failing with the apparatus? Lots of things can go wrong. There could have been contamination while loading bed or doing the backwashing. Short circuiting of the flow. So for example, if you have desaturation of your media, that the air gets entrained in the media itself, and when the flow continues, you can have it short circuiting, so you don't get the full bed contact that you were expecting. Okay, possible, I mean, not likely, but you can't discount it entirely. Incorrect bed volumes, feasible. I mean, all of these things, they're very unlikely. Incorrect flow rates, sidewall flow, it's all possible. I mean, it's impossible to completely remove the sources of error here. But the thing that we keep coming back to is that why are we only seeing PFOA? If there was any kind of error in the apparatus, one would expect that whatever breakthrough you're seeing would reflect the chemical makeup of the influent water. So if you had short circuiting, you should be seeing all of the compounds, not just PFOA, but it is exclusively PFOA that is coming through here repeatedly, time and time again. So, I mean, you can't discount it entirely. It doesn't seem plausible that there is some kind of error. And, you know, as I mentioned, we've run dozens of these with identical apparatus around the world. Never seen these kinds of results. Sampling error. Okay, again, if you were to have some kind of sampling error that has some kind of cross-contamination, one would expect to see it on both the IX and the GAC. I mean, they're literally on opposite sides of the same apparatus. If you're seeing this consistently on one side, but not on the other, and by the way, it was not ECT2 that was running the sampling. This was an independent consultant that was doing all of the sampling. So we had nothing to do with this. So it doesn't seem plausible either that the sampling could be the cause of these results. Blinding agents. So if you have certain chemicals in the water, chlorides, TOCs, these have significant impact on the adsorptive capacity of the media. So maybe there's some mystery compound in this drinking water that, it's causing the GAC to perform poorly. But again, that does not seem very plausible because the blinding agents that affect GAC should also be affecting the IX. So it can't completely remove that, but if there's any thoughts on what blinding agents we should look at, as I said, we have long-term analyses on 196 different compounds. So bad batch of GAC, that's where we were going to the first two trials. I mean, after the trial 2, that's what we kind of assumed. It seemed to be the most natural reason, but almost identical results with a completely different GAC from a completely different manufacturer. Not plausible that we'd have that kind of bad luck 2 times in a row. Now we get into the ones where, there may be, insufficient contact time. Now, on the one side, we've run these kinds of GACs and exactly these GACs with the 5 and the 10 minute contact time and multiple dozens of pilots. We've never seen this kind of behavior. Now, at the same time, the companies do recommend a longer contact time, so recommending 20 to 40 minutes. Potentially, again, why do we only see the breakthrough with the PFOA and nothing else? It doesn't seem plausible. Could be, I don't know. And the final one that I think is the most interesting, and this is something that one of the carbon companies brought up, was that this could be a function of the extremely low, relatively low concentrations that we're seeing on the influent. From our end, it's not common that we do pilots with water that already qualifies the drinking water standard in Sweden is 90. Now it's voluntary, but that's still where it's at. It's 90. Here we're seeing 20 to 50. So it's uncommon for us to be running pilots with influent water that is at such low levels initially. And I mean, it seems counterintuitive, but could there be something going on here that the very low concentrations, we're also seeing extremely low concentrations in the breakthrough, obviously the single digits for weeks on end. Those curves look very dramatic, but keep in mind that it's, single digit nanograms per liter. So could the very low influent concentrations be an explanation of why we're seeing this kind of behavior? So really, this boils down to what is more likely. Are we seeing some kind of experimental error? And if so, what is that so that we can fix it? Or is this a real effect, that is a function of GAC's adsorptive behavior with when we see PFAS concentrations at these very, very low levels? So here, I know we're not allowed to ask questions at this point. I know that we're limited to having the Q&A at the end, but I'm leaving my email address up here, jklewis@ect2.se. And if anybody watching this presentation has seen this kind of thing before, or if you have some kind of a plausible explanation of why we are seeing this, please let me know. I would love to be able to, figure this out and drill down on what is going on here. So that's what I have. Yeah, I've got, I think, a minute to go here. So Edith, there's I'm good if you are.
Yes, sir. Thank you. And there's some questions in the chat. Even I added one.
All right. Well, are we allowed to go through them now, or do you want to hold them?
I think we're going to hold on to them, but in case people keep writing, maybe you can take notes of them.
All right.
Thank you.
I'm just going to mention here. Sorry, before you cut me off. It's my daughter's birthday. I'm not going to be able to stay around until the Q&A. So please, if you do have, please get in touch by email. That'll be the easiest thing. So please jot down the email address you see at the bottom of the screen, and I appreciate any feedback. Really, really do. So thank you very much.
Happy birthday to your daughter. So our next speaker is Anna. Yeah, it was, we had someone before, but it's Anna Defina. She's an environmental engineer based in Golders Milan office with over 15 years experience as an environmental professional. Her main expertise fields are remediation design, sustainability studies, and human health risk assessment. Over the years, Anna has expanded and enhanced her technical expertise and interest for innovative, sustainable remediation techniques, mainly bioremediation and in-situ injection of remedial reagents, and is a registered professional engineer. So welcome, Anna. She'll be talking about a case study on sustainable remediation of PFAS impact at an active fire training ground using passive, cost-effective methods. Thanks for being with us, Anna.
Hello, everybody. Thanks, Edith, for your presentation. I work for Golder Associate, and I'm going to show you this case study of a sustainable remediation of PFAS impact in an active fire training ground using passive, cost-effective methods. This is the background of the agenda of this presentation. We go through the background of the project. We'll describe the environmental investigation undertaken, the remedial objectives that were the driver of our remediation option assessment. We will describe the assessment itself, the remediation trials that were undertaken, and finally, the selected remedial strategy. This is the project background. Golder was engaged in 2018 to evaluate the different remedial option for PFAS in an active fire training ground where M foam was used. The purpose of this presentation is both to share with you the process of selection of the remedial option, but also to discuss how in certain cases, certain projects like this one, while everyone is investing in high-tech technology to remediate PFAS, in some project, existing low-cost passive civil solution can also manage to reduce risk and achieve the project goals in a shorter time frame. The site is in Victoria, Australia. You can see the red areas are concrete pads with the steel props where fire training exercise occurred. Water used for extinguish the fires were collected to the blue lines, which is a drainage system, an open drainage system in concrete, through some interceptor pits where foam and fuel were separated from the water and then collected to northern separating tanks before being pumped out to the municipal sewer. Apart from the concrete pads, the site is unpaved and it's unbounded. This was an issue because some flooding events occurred and the water entering the site got enriched in Pfas contamination that flowed out from the site and could spread contamination in the surroundings, both in groundwater and in the surface water system. The area is a rural area with channel and field for cattle. Going to the environmental investigations, overall, more than 400 samples were collected at the site. The greater effort was on the surface soil and cover. So concrete cores were collected, both superficial samples were analyzed, but also deep concrete cores in order to create a slab profile and contaminants concentration. Soil were collected and analyzed, both for total PFAS and for the leachate concentration. Sediment from drainage channels, pits, and separator tanks were collected and analyzed. Foam storage vessels, and the concrete and steel prop runoff water. In all these matrices, PFAS were found in high concentration, but also groundwater and surface water were monitored in samples, and some detection were also recorded in groundwater. The goal of the remedial option were, of course, to provide no acceptable risk to beneficial uses, to comply with the guidance Australian documents, to minimize the potential for human exposure and thus the risk of to human health. And as I mentioned before, to minimize the risk to the environment, reducing PFAS mass discharge to the environment via surface water or groundwater because of the runoff water coming from the site. And another goal was that the remedial option needed to be practically implemented, because we all know many of the technologies to remediate PFAS are still an experimental emerging stage. In this slide, I'm showing you the different options that were assessed for soil. It was analyzed the complete removal of soil across the site, the partial removal of soil hotspots, the encapsulation of soil using the capping, and reducing the PFAS impact in runoff water using a soil binder in the soil, and also creating a band across the site. While for concrete, which is an issue at the site, again, it was assessed the option to remove all the concrete at the site, a partial removal of hotspots, the sealing of the surface using a concrete sealant or capping the surface with a new concrete surface. It was also set pressure washing via sandblasting or ultra high pressure washing. And also for the concrete tank, the use of pre-made drop-in liners. We have a lot of impacting matrices. So for steel props, which were impacted by PFAS, it was assessed the complete removal of the steel props or the removal of only the outer layer using high pressure blasting or sandblasting. Water, runoff water impacted by PFAS. The remedial option which were analyzed was the collection and treatment of PFAS water leaving the site, or the use of in situ passive treatment within the drainage channel, like the use of rimbind of a similar aggregate. At the end, this option was discarded because water was not only impacted by PFAS, but also by kerosene, and the fuel will absorb to the activated carbon of the rimbind, and thus it was not effective on the PFAS. A quick description of the trials. The trials were focused on the concrete because it was challenging to find a solution, and they were impacted. Some treatability trials were conducted to assess if waterproof sealant could be effective. Cores were treated and then tested. Surface leachability testing was conducted. The results were quite interesting, but the high temperature can be an issue. And as you can see in the picture on the top, during the fire training exercises, the temperature in the concrete can rise up to 500 Celsius. So at the end, this option was retained only for the concrete tanks and the concrete drainage channels. On the table on the bottom right are the results of the pressure washing trial, which was conducted mainly to convince the client that the concrete was a porous media itself. So the pressure washing couldn't be not effective. And as you can see from the numbers, actually no reduction was obtained from this trial. So the option was discarded. This table summarizes the remedial strategy selected at the end. In order to mitigate the impacts to surface water and the groundwater from the site, it was first decided to build an earthen band across the site. For the impact due to the soil, it was decided to remove only the hotspots while keeping all the site, all the unpaved side. So the goal was to mitigate both the liquefaction of contaminants to groundwater, but also the human health risk to the direct contact of PFAS in topsoil. Regarding the impact in concrete, it was decided to cap the concrete surface with a new concrete slab and to use the sealant only for the concrete tanks, thus reducing the overall the PFAS concentration in the runoff water. Another action that was undertaken was to remove the impacted sediments from the drainage system and to cap the open drainage channels with a new concrete precast channel, while no action was at the end undertaken on the steel props. A bit further discussion regarding this identification of the hotspots and the rationale behind. It was assumed as a criteria, the industrial commercial screening criteria for total PFOS and PFHXS as a screening level. And as you can see from the graph, the soil sample having concentration higher than the criteria are also the sample having the highest concentration in leachate. And overall, the threshold limit in leachate is quite high, more than 400 micrograms per liter, which is high, also compared to the criteria in groundwater, at least in Italy, but I believe worldwide. But it was accepted because perched groundwater was a seasonal aquifer with no usage in a very silty clay matrix. So the environmental risk and the human health risk was very low. And also the soil that was not excavated was, however, kept. So the excavation risk was very low. This is the modeling where you can see the 3 hotspots that were identified, and in the table below, an exercise to show you that with the removal of only 500 cubic meter of soil, the mass of PFAS removed is more than 30 kilograms. Still remains 58 kilograms of PFAS at the site, but to achieve the complete removal, the overall volume of soil that needed to be excavated is more than 1 order of magnitude higher. Thus, the cost and the sustainability of the remedial action was not feasible. Going to the conclusion and to some sustainability consideration, through this project, we were able to extend the life expectancy of the infrastructure without generating concrete waste nor removing steel props. During the remedial activity and investigation, the operation of the facility was not interrupted, so good for the local employee. And also the materials were supplied from local suppliers in order to create a benefit to the community. Overall, the cost for the remediation was $7.5 million, which is far lower than the estimation for the commissioning and rebuilding of the facility, which was estimated in $37 million. And I conclude with some picture of the actual remediation, the new capping of the concrete, the capping of the soil, and the sealing of the concrete tanks. Recently, we got results of runoff water after the remedial activity was completed, and the concentration decreased of 3 orders of magnitude compared to the one before the remedial action. Thank you, everyone, for the attention.
Thank you for a great presentation. I guess we're holding on to questions until the end. So we have our next speaker. Our next speaker is Helena. I don't know if I want to say your last name correctly, but Henriksen. She is the founder of Envitech Solutions, and she is currently the head of the R&D. She has a bachelor's in environmental engineering and has been in the industry for 13 years, working as a remediation specialist and entrepreneur. She has a burning passion for solutions to the PFAS problems, which is the reason that she has been carrying out both the first and the large PFAS stabilization projects in Europe, as well as the shining light on the SAFF treatment method, bringing the SAFF technology to Europe. Welcome, Helena. She'll be talking about surface active foam fractionation, SAFF, effective PFAS removal from water using only air. Welcome.
Thank you.
I love your shirt.
Thank you. I'm just going to go into presentation mode, but you are in the way. So there we go. Good evening, Remtech. Love your show tonight. As a European, I was always wanted to say that, so that felt good. My name is Helena, and I'm here to tell you about the SAFF method. The outline of my talk will be a quick repeat of the nature of a PFAS molecule. Won't bore you because I know you're all experts. A history of the SAFF. What is the SAFF and how does it work? We have results from the first 2 full-scale projects with mobile plants. And yes, I will also tell you how much this treatment is costing you And at the end, for you to remember everything that I said, I have brought you a summary. I said if we have time, I show you more results, but I'm pretty sure that we won't, so unfortunately. PFAS, as you know, so many, so severe, but yet so different. We have the precursors, species of perfluorinated substances and polymers that become, for example, PFBA and PFOA when oxidized. We see this in our process, and that's why I highlight it. We usually talk about short change. We call them C6 chemistry and below, and they are more soluble, hard to catch, and that is the same for every treatment method. So it's not just for us, but it's also for us. Long change, C6 chemistry and above, less soluble, easier to catch for everyone, also for us. So that's just a short. The PFAS molecule, as you all know, it has the red head. It's always shown as a red head, so I love that, since I am one, that it loves to be in the water. And it also has a tail, which is a hydrophobic tail, which hates to be in water. And we use this when we do the SAF, as the bubble becomes the perfect holiday resort, the perfect environment for PFAS. So PFAS with a long sticky tail sort of adds on to the bubble, sticks its tail in there, and the head gets to stay in the water and get absolutely happy. And by bubbling bubbles through water, we therefore lift the PFAS up and be able to recover it as a foam. So that is sort of the short explanation. Shorter chains have a shorter tail and they don't really stick that good to the bubble, but we still bring them up a fair bit and we call them top section swimmers. So I'll be mentioning them too. SAF, surface active foam fractionation, is developed by OPEC Systems in Australia, and as a result of a grant that they got from the Australian Defence. They did some research for 5 years, and then they first commissioned the full-scale plant in Oakey in Australia in May 2019. I managed to meet and fall in love with OPEC in September 2019. And as I saw this technology and its potential, I was just absolutely in love. And from that, it's been a few years, but we have now the first 2 full-scale mobile units commissioned here in Sweden. The first one in February 2021, and the latest one just like last week. So that's really exciting. The technology, we are in 2 winning grants for EU grants. Horizon 2020, which I think everyone was in. We're very happy to be part of the winning team there. And we're also winners of the Life Source, which is another one that we go through Spain and Sweden. So super exciting. I am here instead of OPEC because Envitech is the exclusive retailer for SAF in Scandinavia. And it's my project, so I get to present them. So SAF, I told you we used bubbles as physiochemistry as the perfect environment for the PFAS to get them out of solution. And we do that, as we said, by bubbling air bubbles through a column. So we do it first, as you can see in the top corner once, and then we remove the PFAS. And that's actually the first treatment step and only treatment step. In the second step and the third step, where we do it all over again, that is just concentrating the waste, making it a minimal waste solution option. Total concentration that we can get is between 500 and 200,000 times decrease in volume from the initial concentrations. So this is like the inside of it. So we have here, if I don't know at the point, but we have a feed water storage tank that starts as that gets full with water. That kicks off 4 primary reactor vessels, as you can see here, the 4 big ones. They work like pistons in a car, so they are not in series, they're in parallel. And as one fills, one empties, one runs. So it's a continuous inflow and continuous outflow, but we still do a bit of a batch principle. After that first treatment is done, the water is treated from PFAS and released to recipients. And then we do it all again in these smaller vessels. The secondary fractionator is the second picture to the right. And then the third time in these third vessels, which is the third picture. Really hard to comprehend how this works, so I will actually show you because it's so much easier to see. So what you see here is the magic foam that gets there when you bubbles through water, and we bring up the PFAS to the top, letting it spill over and just get removed. At the end of this, we do a push with treated water, and that is to get those top swimmers out of the water and also get them. So we get a bit more PFOA or the short chains, I mean, by doing that. So we get a lot better treatment. The next step, the secondary, looks like this. Here we take the PFAS that we removed and we are concentrating it in a bit of a different treatment method. So here we have about 1,500 times the concentration factor that we had initially. And you can see that's a totally different foam. Third one, well, you can just see that this is nasty and that it's really high concentrations that we're working with. You can just, yeah, basically see that just go up. When we do this, we have different treatment methods. PFAS and PFOA, we've seen that come out in about 3 to 4 minutes. PFHXS has a bit of a longer time period, and we found a bit of a sweet spot at 19 minutes. That's when we get the most PFAS out for the least energy consumption, because that is the only thing we use except air, it's electricity. So this is what it looked like in the beginning 2 years ago. This is the first full-scale plant in Oki. It's been treating 50,000 cubic meters of groundwater. It has reached the target ever since, which is 70 nanogram for PFAS, PFOA, and PFHXS, the sum of them. It has not exceeded any guideline levels in 2 years. And from 50,000 cubic meters, we have produced 10 liters of PFAS concentrate. From day one in Oki, they have measured 30 PFAS or more. And here you can see the sort of levels that gets into the SAF, what comes out of it, and what's actually get treated by carbon or an ion exchange mass. The ion carbon is at the end, well, OPEC used that because they didn't really know that was going to work the first time they set up this post-scale plant. So they put that at the end, but they wouldn't have needed to meet the targets. It's just been working since day one. And from the results, they have done a removal model that you can see here to your right. And there's sort of a summary of the percentages. That's actually the Swedish 11, because that's what we use for PFAS here. But the removal rates for them. So here we can see that we remove the long chains, really great percentage, but we do not do so good on the short chains, which was expected. So I came to Australia, fell in love with it, and I said, oh, I want to take this to Sweden. I needed in my project. How can we do this? And they said, oh, well, we can build you a bench scale model. And I said, yes, please. And so they did. And so I left Australia and I got these little peas with me. It looks pretty simple, but it works really great. And as I came home, I got offered the chance to be in the Environmental Institute of Sweden. They were doing a research for good PFAS treatment methods for leachates, and asked me if we wanted to be a part to show the SAF model. And I said, yes, of course. So we went there and we got to trial the little unit on 5 different leachates from all over Sweden. And these are the results that I got together with IVL. So in the first column, you can see the PFAS substances. Second one, you have the number of carbon atoms. Third one is the OPEC prediction model for groundwater, which was the only water that we had treated full scale before this. And then in the fourth column, you can see the results that we've got in this little model that we've got. And you can see the results. We were just as blown away as I hope you are now, because we got so good removal and almost perfect as the prediction model, which was really happy since it was a study done by the IVL. Andre had also put in the last column, which just shows the half-life in the human body in years. And I thought just that was interesting to put in there. You can see that by SAF, we remove all the substances that has a long half-life time in the human body. So we thought that was pretty cool. And at the time that we got the results, I've kind of entered a public procurement project for a leachate in landfill, and I actually managed to win it. So welcome to Telge Återvinning, where we have commissioned the first SAF plant in the world. Let me tell you that this water is absolutely love it and so hard to treat. So many different methods have been trialed but failed. So it doesn't have that much different than normal leachate. It's got everything and anything, metals, oil, phosphor, anything. I've done a bit of a summary up to the right. You can see that we have PFAS and PFOA, 250 plus 100, and then we have a lot of suspended particles, TOCs and DOCs. But they also have these algae, and they have lots of it, and they've sent it for analysis, but it has a no name. I have named it the ghost, because you can see it, but you cannot touch it however you do it. You try to get it, but you can't. So that was like an extra adding to that project. And but we have won it, so there was nothing to do but to just jump into it. I held my breath, I must say that. But then COVID hit, And as you know, it affected us all, and it affected the transport of the SAFs to Sweden. But the project has to start. So the client asked us how we was going to do that. And I said, well, let us have a good try with carbon and see what we do, and just to compare it to the SAF later on. And so we did. I put up a two-step mixer. We had some we had a flocculant and precipitation that was tailored for this algae. We had lamella clarifier, 38 cubic meter sedimentation tank, 1,500 kilos carbon just to knock out the DOC and all that other stuff that was in there. And then we thought we were going to have carbon for the PFAS. Well, that only took 4 days to go through, and then everything was blocked, and the PFAS was just as high in as out. So that didn't work really well. But we were thrilled when in February 22 minus, the Australian plant came. So that was, yeah, that was a bit of a challenge, but we got through it, and we commissioned it in less than a week. And finally, we got to do the full-scale results. And here you can see the substances. You can see the removal rate from OPEC prediction model. We did a little trial in the mini SAF, which I put there too. And then you have the removal rates in percentages for each substance in this leachate. Here now, we have no pre-treatment method, no nothing. We are just taking the leachate and it goes straight into the SAF and then straight out. Target for this project was 50 nanograms per liter Pfas. We get that really well. And we have a flow rate of about 20 cubic meters an hour to meet a yearly flow rate of 120,000 cubic meters a year. This slide I just threw in there for those who want to dive into concentration, see what we have in and out. You can see that we really reached the PFOA and PFAS really well. And you can look at that later on when you have the presentation in front of you. It was just to put it in there.
Helena, I'm sorry to interrupt.
Yeah.
I'm sorry to interrupt you, but I think you over the time, and so just letting you know.
Yeah, okay, I thought it was 15 minutes. Now it's 12. Okay, fine. I just want to show you that we have a lot of algae. And yeah, that's pretty much it. We have a second plant going, and that works really well. And for costing, because I promised you that, we can finish off with that. It is about 0.1 euros per cubic meter treated for the leachate, which is great, fantastic, and about an 8-hour service technician a month. So that's about it. So I'm sorry for going over time. And if you want to know me more, just contact me. I'm on LinkedIn and email and phone. Thank you.
Thank you. Yeah, I think it said until 50, but if you started, I'm sorry, I interrupted you. And we'll wait for the Q&A session after all the speakers have gone on. We have our next speaker is Mr. Stefan Hitman. He's the founder of Sensate company, Sensatech company, based in Germany. He's a microbiologist and a soil scientist, and his company is heavily engaged in research activities for the remediation of PFAS contaminated soil. He will be talking to us today about in situ and on-site remediation of PFAS contaminated soil. Welcome, Mr. Hitman.
Thank you, Edith. Let me share my screen. There we go. And I hope can switch it to presentation mode now. Do you see my presentation now in presentation mode?
No, sir. We'll see you. Or I see you.
Now it should work.
Now it's black, but I think it's loading up. There it is.
Okay, great. And it's in presentation mode. Yeah, okay. Yes, I would like to share with you some findings for the development of an in situ remediation method for PFAS contaminants in the VADOS zone. And I'll go with you through the process from lab experiments to field application. And I would like to also introduce my co-workers, either Anya with my company, and then also our partners from Geologic, which are based in Münster, also in Germany. First, I would like to introduce you to the site, then our remediation concept, the lab studies we did, and then the field tests and results. And before I reach some conclusions. The site is quite a fascinating one, probably the most widespread PFAS contamination we have so far in Germany. It's very close to between the German and French border in southwestern Germany. Originally, the site is close to Baden-Baden and Rastatt in southern Germany. There's PFAS contamination of agricultural topsoils, which originate from compost, which have been produced by composting paper sludge, which was heavily contaminated with PFAS. And that has been offered to farmers for free as a so-called soil conditioner. That has been applied for some years. Now we have, in average, we have PFAS values of about 270 microgram per kilogram. And they have been persistent in this area for more than 10 years. And they gradually elute into the Rhine River, which you see on the top left-hand side of this aerial map. So our remediation concept was based on an elution of PFAS from the topsoil and then collecting it in a rather shallow groundwater, which you will typically find in the site, and then eliminate the PFAS from the water. This would all happen under very carefully controlled hydraulic conditions. The dig and dump technology in this case was no option, because in this case you would definitely destroy the farmland. So the idea was to preserve farmland and allow farmers to make use of their agricultural areas again. So without destroying the soil in its composition. And especially not eliminating the topsoil where all the PFAS were accumulating. So we did very extensive lab studies. The idea was to use a biopolymer which would effectively bind to PFAS and then use this as a substance to help eluting the PFAS. We did PFAS elution tests and the flotation tests and measured different types of soil physical parameters. Then we went to upscaling in the mesocosms. Basically, we made use of a lysimeter. I will tell you more details about that later. Before we went into constructing a remediation unit and a water treatment unit, because we eventually intended to recycle the water that we were using for the soil washing process. And then in 2020, we did a 3-week field test in the Rastatt area. The first step, the investigation of various polymers, were done with our partners of the Technical University of Berlin. We did structural analysis of different types of biopolymers. Basically, all these biopolymers had surfactant characteristics. So we identified, among others, the critical micelle concentration, density, viscosity, and also toxicity, because eventually, as I mentioned, this was one very important aspect, not to destroy any central characteristics of the topsoil. Here's some examples of the elution tests that we did. Just as a side information for you, in Rastatt, they did a lot of analysis of agricultural products that would derive from these affected sites, and they found rather high values of PFAS in plants that would, or especially in the fruits, that would contain a lot of proteins. So protein were one of the biopolymer parts that we made use of. And then we did, it was basically an optimization by doing numerous and uncountable elution tests. We used disturbed soil samples from the Rastatt area, and then we optimized the elution by adjusting and changing pH conditions, the biopolymer concentration and its structure, and before deriving at the best performing biopolymer application. We also investigated on foam characteristics, because eventually when we extracted the groundwater, this would still contain the biopolymers, which we wanted to extract by foam fractionation, maybe quite rather similar to what Helena was just showing us. We optimized the flotation parameters, and we did some upscaling in a small scale application. We in very short application times, we reached 99% removal for the PFAS elution from the water phase. But back to the soil treatment, the next step was after we did a very had very positive results from the lab scale. We went into the technical scale for a proof of concept. Now this time using undisturbed soil samples by an array of 3 stacked metal rings. We did PFAS analysis of the soil before and after the elution, and we analyzed pore water by suction cups. Here are some pictures of it. You see the left-hand side, this metal ring that was extracted and lifted by a truck or by an excavator from the soil. And in the central part of the pictures, where you see how these rings were applied, or how water or surfactant containing water was applied, letting it elute through these stacked rings, and then using suction cups in each of these rings to gather soil samples to analyze for PFAS and for biopolymers. Yeah, here's now going to a full scale. We designed and built a treatment unit for the water that was being collected on the site after the elution, directly below the area where the biopolymers were applied. You see on the left-hand side these 2 reactors, as in it is again a sequential batch operation. So one tank will be filled while the other is actually being treated, so we can have a continuous operation here. Again, you see these transparent parts of the tube, so we could always check for the foam to develop and to be transported through the system. There's the setup of the area. We had an active carbon filter just as a backup the system. So if since this was still a research project, if any of these treatment parts would fail, we would still have the granular active carbon as a backup system. On the right-hand side, you see the foam running through the transparent tubes to this collection tube. Here's some results. In the lysimeter, we managed to see a 99% PFAS removal in the soil that was being treated. And in the field test, eventually, after 3 weeks application, we had an 80% PFAS removal. We would have gone on with the treatment, but then winter came, and we didn't have a plant that was suitable to sustain winter. Certainly, they would not be as bad as in Sweden, but in this case, even northern Germany or central Germany can become pretty bad. So we shut it off for security reasons. Eventually, we ended up with a successful development of an innovative new in situ remediation strategy for the removal of PFAS from highly contaminated topsoils without completely destroying the soil structures. We are only using natural and biodegradable materials based on the protein structures. And it was possible in this project to deliver very satisfactory results within a rather short time frame. Yes, I'm also going to talk about pricing. It is, at least in Central Europe, it's extremely costly to remove and dump PFAS containing soil, because all the waste disposal site owners know that the PFAS will never make it through the water leachate treatment system. So they simply refuse accepting these soils. So the only thing is disposal in hazardous waste dump sites. And if you add up all the costs, including transportation, you easily end up with cost, as indicated here, of 250 euros per cubic meter eliminated. We can reduce that considerably, and further optimization tests are underway in form of a new research project that I'll just show in the last slide. We can perform feasibility tests in the lab within just a few weeks to identify PFAS mobilization sites specifically. We have a pilot test plant that is available for tests on site, and we can easily do upscaling by using agriculturally based technologies. The outlook is now underway in form of a newly established research project that will focus on on-site remediation, because we know that there's lots of soil material that is still waiting for any kind of treatment because it is so hard to be disposed of. We will use the same array of biopolymers from concentrates, and we are also working on a desorbable granular active carbon system that will use electrostatic processes to adsorb and then desorb PFAS and again form PFAS concentrates, so we can recycle this water and the biopolymers. And that's underway. It has started in March this year, and it's going to continue for another 2 years. And I will be happy to present it to you in maybe next year at the Remtech Europe. So thanks for your attention. I'll be happy to answer other questions, and I hope I managed to stay in time. Thanks for everyone.
You did. Thank you. Yeah, Q&As will be toward the end of all the presentations. And I think now I pass it to Wouter. I'm sorry.
Good afternoon. No problem. And you did a great job. We are on time, so I hope I can do the same. Anyway, the next presentation will be about the use of colloidal activated carbon to treat PFAS in a fractured rock aquifer. And the presenter will not be the person that is mentioned. I believe it's not Rick McGregor, but it will be Rick McGregor. I like the mistaking your name, Rick. Rick is the Senior Technical Advisor at In Situ Remediation Services. It's a Canadian company. And he's a hydrogeologist, also geochemist from the University of Waterloo. And he has worked in groundwater remediation of over 20 years. So I believe he's the perfect person to present this case. The floor is yours, and we see your screen.
You can see my screen?
Yes, indeed.
Great.
Well, a copy of it at least.
Okay. Thank you very much, and thank you to the organizing committee for accepting this talk. Today, we're going to talk about the use of colloidal activated carbon that was injected into this is a multi-complex aquifer system, including a fractured bedrock aquifer itself. I'd like to thank my co-author, Ms. Benito, and we'll get right into it. So I'm not going to spend too much time on the background of PFAS. Everybody listening here has probably had enough PFAS for a while. So, but that said, there are some things that make the in situ, make treatment of PFAS in general challenging, and make the in situ treatment of it very challenging. There are thousands of compounds, of which most of us have not seen any analysis or know much about the toxicity of it, so it's hard. The carbon fluoride bond is very hard to break, and therefore it's not really amenable to a lot of in situ methods that are currently used for a lot of compounds. There are a lot of analytical challenges, which make analyzing PFAS in general, and the health advisory levels all over the world are changing literally by the day or week. But generally speaking, most are going down to the tens or below 10 nanograms per liter. And to make this really complicated for in situ treatment is the fate and transport of the PFAS compounds is not well understood at all. It's evolving now, and there's lots of studies and research studies being done, but it's still fairly complicated compared to other compounds. In situ approaches being used right now are, well, it's a short list. There really is only one that has been proven in the field, and that's colloidal activated carbon. And it's only been limited approval, but it has probably 20-25 sites now around the world, mostly in North America, but some in Europe. But they haven't been in the ground for long. The longest one is a study that was being done in Canada here that's just past 5 years. Under development, there's ion exchange resin, which shows very good promise, biochars, powdered activated carbon. And then there's the more emerging ones, the soil chemical, the foam fractionation, which we just heard it talk about above ground treatment, but there are people looking at below ground. And there are people who are looking at the oxygen still. This is a really summary of what's been done for colloidal activated carbon in situ to date that's been published that I'm aware of. Unfortunately, my name shows up a lot on this. The first study was done about 5 years ago in Canada. Like I say, it was an accidental. And all these plumes were co-mingled, usually with petroleum hydrocarbons. But the third study down there was a study done in China that was done with TCE and its breakdown products. The limitation on this has been that they haven't been studied for that long. The most here is 5 years. Most are 1 to 2 years. The aquifer types have differed a bit. But the one I'm going to talk about today is the one that's right at the bottom. Actually, it was just published last week, so you can change that to 2021. And it was really a complicated aquifer system. So very basic, simplified diagram showing the aquifer system here. So at the top, you have a silty sand glacial till. It overlies a sand unit, which overlies a fractured dull stone bedrock. The hydrogeology in simple terms is, so we had a 3 aquifer system. The first one, the silty sand had a hydraulic conductivity about 4 times 10⁻³ centimeters per second, which is typical for a silty sand till. This site was also in Canada, so we have a lot of glacial till like Northern Europe. The groundwater velocity, give or take, was about 10 meters per year in the silty sand. Underneath that is a sand layer with very conductive, or made to more conductive and a higher groundwater velocity that reflects that. Underlying that is the fractured bedrock. We did a lot of testing to look at the fracture zones within that bedrock using packers, isolating packers, and we found 3 main zones, fracture zones, with equivalent hydraulic conductivity shown there, 10⁻⁶, which is the bulk host rock, and then right up to 10⁻³ equivalent transpersive hydraulic conductivity in the fractures. The graphs on the right of your screen just show the hydraulic conductivity, the minus natural log of the hydraulic conductivity of the silty sand overlying the sand, which is the hash unit, overlying the fractured rock. So in the fractured rock, you see big variabilities. The units here, basically, as you approach 0, it's the higher hydraulic conductivity. So you can see 3 higher hydraulic conductivity units in the bedrock itself. This study, we analyzed a lot of different chemistry at the site, but I'm just going to, for time's sake, keep it pretty basic. We analyzed 28 PFAS compounds. We detected 5. This site, I also should explain, came on the radar because there was a little industrial facility, and the firefighters, it had a fire, and the firefighters used a foam to suppress the fire. Within that foam, obviously there was some PFAS. So when we were brought on site to help clean up main case here was the petroleum hydrocarbons, we also decided to take samples for the PFAS compounds. So we had 5 PFAS compounds. None of them were very high detection, except for the PFP-EA, which was about almost 13,000 nanograms per liter. But most were very relatively low level, and we only really found 5. So a very defined PFAS plume, if you want to call it that. And we did have BTEX, benzene, toluene, ethylbenzene, xylene within the water as well, at concentration of about 4 to 5 micrograms per liter. On the left here, you'll see a schematic of the monitoring system that we had. So heavily monitored, the scale there is on the right, or sorry, on the left, and you'll see CMT stands for a channel multi-level. So that's a special type of well that has a 6-inch screen. So we had basically 3 screens within about a 2 to 3 meter aquifer thick, so vertically. So we could vertically very accurately define the plume as what coming in. So groundwater flow here was left to right. So CMT1 was installed in front of the treatment zone. And the treatment zone here would be kind of a permeable-reactive zone or permeable-reactive barrier. So we want to stop the water flowing off site. The barrier started at CMT2 and then it just passed CMT3. I should have put that on there, sorry. So we had lots of monitoring locations in the unconsolidated aquifer as well. Within the fractured rock, we had 2 zones, Packer isolation zones that we had installed in boreholes. So this slide just kind of explains what we did here. The other thing is we took multiple cores of the aquifers themselves to look at before and after injection. We wanted to see where the activated carbon or the colloidal activated carbon was being injected into. So we took lots of cores to look at that before and after. The material well, we'll get into that. We also sampled a lot for the general chemistry, as well as volatile organic carbon compounds and the PFAS. We did 4 sampling events over a 1-year period, basically a pre-injection, a 6-month, a 9-month, and a 1-year post-injection event. So the injection program here, as I said, we used the colloidal activated carbon, which is sold under a brand name called Plume Stop, manufactured by a company out of the US called Regenesis. In the silty sand and sand units, we injected using direct push technology. So we advanced down rods and we used a 2.5 meter grid. And over that grid, we injected within each aquifer about 15,000 liters of the Plume Stop solution at a 10 weight percent. That's a pretty common concentration to use. And you'll see the volumes here, masses that we used of that. Within the bedrock, obviously you can't advance direct push. So we used boreholes, and then we used combination packers to actually inject into the target fracture zones themselves. So once you're in the results here, the distribution, first thing we want to look at is the distribution of the activated carbon itself. Obviously, if in situ programs, it all comes down to contact between your reagent and the contaminant. If you don't have the distribution of the reagent, you're not going to get any treatment. So the first thing we did was took cores before at 3 locations. Those are represented by the black dots. Basically, it was all almost at the detection limit for the, in this case, total organic carbon. That's how we converted the activated carbon. So you'll see that there, the average was 0.5 grams per kilogram, which the detection limit is 0.05. So basically at the detection limit before injection. After injection, we took samples from the unconsolidated aquifers, and you'll see here that you see a drastic increase, almost an order of magnitude increase. You also notice here at the depth of 4 meters, we had a sand seam within the silty sand aquifer. In that sand seam, we see an enrichment of the activated carbon that we injected, which is expected. In the sand below that, we've seen a relatively uniform distribution. Overall, we've seen about a 200 to 300% increase in the TOC concentrations post-injection. So the results here, these are a little bit complicated, overwhelming graphs, or plots. These are cross sections of the plume. The top, there's 4 graphs here, or 4 plots. The first one is pre-injection, and then they go down 6 months, 9 months, and 1 year post-injection. What you see here, groundwater is flowing left to right, and as you see the groundwater enter, which is into the barrier zone, which I should have put on here, which starts at about CMT2 and goes to CMT3. At the top, you see relatively uniform distributions of the PFAS, in this case, PFBA. And after we inject it, you'll see complete removal of the PFBA at 6 months, at 9 months, and at 1 year in all 3 aquifers. So the reason you have a different curve between blue and green is the detection limits vary depending on the aquifer we were sampling from. But basically, all the concentrations were in the fractured rock were either less than 5 or less than 10 nanograms per liter. So we had complete removal post-injection up to 1 year of the PFBA. The PFPEA, which is more of it's a little bit longer compound, is 6 carbon. Once again, you see a relatively it's a stratified distribution pre-injection with higher concentrations in the shallow groundwater. But post-injection, once again, we see good treatment, complete removal at 6 months. However, at 9 months and 1 year, we start to see breakthrough within the shallowest fracture zone in the fractured bedrock. And you can see that by the Packer 1 or Packer 2 top sample there at a depth of about 9 meters. You'll start to see that yellow indicating we had breakthrough. We didn't see breakthrough in the deeper fractures yet, and we did not see breakthrough within the sand aquifer, but we did see it within the fractured.
Rick, sorry to interrupt you, but time flies.
Oh, okay. I can. What you see similar things. The BTEX, we had complete removal. So on the findings is we had great removal at three months. BTEX was removed for greater than a year. The carbon was distributed well, but we did see breakthrough of the C4, C5 carboxylic acids in the fractured rock. We did not see breakthrough of the sulfuric acids. So finally, I'd just like to thank the academic and our partners here. The academic partners are University of Waterloo, University of Toronto, and Carleton, and then our industrial partners, Polar Water Solutions. And I guess that's it.
Thank you very much for this interesting presentation on the use of GAC and plume stop. I know there's a lot of discussion going on about the product, so I really appreciated your presentation, and we will come back to it, I suppose, in the panel discussion as well. I would like to jump to the next presentation. It's about compound-specific stable isotope analysis to determine sources and sinks of PFAS. It will be given by Kevin Kunze, and he has bad luck. I introduced him already, I believe, yesterday or Monday. It should be Monday. Kevin is the lab manager and innovation expert at IsoDetect in Germany, offering isotope analytical services and scientific expertise for stakeholders. Kevin, the floor is yours.
Yeah, thank you very much. And hello again, Walter. Yes, you're right. I think it was on Monday. And do you see my presentation?
Yes, yes.
Okay, something I already
even your laser
something.
pointer. Yeah.
Yeah, but I already paint something nevertheless. Okay, thank you very much for this introduction. And yeah, so I'm Kevin from IsoDetect, as Walter already mentioned. And the title of my presentation is, or I want to explain you how if compound-specific stable isotope analysis is potentially a tool to determine sources and sinks of PFAS. As already, what's going on here in my presentation? I don't know. Somebody is painting. Nevertheless, so already nicely introduced by our previous speakers, we are all aware about this problematic situation of PFAS, about this toxic and recalcitrant and highly mobile properties, creating long blooms within especially the shorter chain PFAS components. We are all aware about the precursors that can be converted to the respective PFAS. And we are aware that's not only P4 and PFAS is over 5,000 different chemicals that are present at PFAS contaminated sites. So there's a high demand on really innovative monitoring tools for site investigations. And so what are those tools to bring, or which monitoring tools do we have to bring light into this darkness? First of all, of course, yesterday we heard there was a really interesting training session where we were introduced in this TOF analysis, Q-TOF analysis, so all this target and non-target analysis by ultra high resolution mass spectrometry. So there's really development going on, really to bring some light into this darkness about this PFAS contamination. Nevertheless, today I want to introduce you in a further possible tool to investigate sources and sinks of PFAS. It's about compound-specific stable isotope analysis. And what are stable isotopes? So stable isotopes, just to introduce you, are really are atoms of the same element differing in the numbers of protons and the numbers of neutrons with the same number of protons. You see here, for example, for carbon, we have a light carbon, it's a stable isotope, and the 13C carbon with 1 neutron more. So we have 2 stable isotopes presented in the nature with a distinct ratio. And this ratio is for carbon about 1% to 99%. And this ratio can be measured for every carbon-bearing compound by high resolution isotope ratio mass spectrometry, and is set it against an international standard. This international standard is a VPDB, it's a carbonate where this ratio, this actual ratio of 13C to 12C is measured, and it's set it as 0 because the difference between the ratios are really small. That's why it was introduced as an international standard, and all the other compounds are measured against this international standard. So all and the difference are presented in per mil. So the difference is when you have negative isotope values or isotope signatures, you have more light 13C and less heavier 13C in comparison to international standard. And when you have positive primate isotope signatures, then you have more 13C. This is just the background, but why do we analyze those stable isotopes? We analyze because every compound, for example, honey, for example, vegetable oil, whatever, and also, of course, pollutants have a significant isotope fingerprint. So they differ because due to production lines, where they would produce, what were the precursors, and so on. And every single compound has depends on how many elements is in the molecule, but has really a distinctive isotope signature. And with this fingerprint, we can do source identification. And a second big advantage of this monitoring tool is it's a tool to investigate if active degradation is going on, or do you have a success control of degradation processes. And the basic is that pollutants pollutant molecules with heavy isotope are degraded more slowly and accumulate in the remaining pollutant pool. And this is due to the situation that the activation energy between a heavy stable isotope and light isotope is higher than the activation energy or the bond energy between molecules that only have light isotope inside. So that's why due to degradation of those contaminants, the residual fraction are enriching in the heavy isotopes, because first of all, shown here by the example of benzene, all the molecules with only light isotopes are degraded by microorganisms, for example. So it's a biodegradation processes, and all the other with heavy isotopes are first then accumulating in the remaining pool. And that's why with further degradation of the contaminant, your isotope ratio of 13C of heavy to light is increasing. So you have a shift in the isotope value of, for example, -30 per mil up to -24 per mil or even higher. This tool has already been applied since the early 2000s at more than 200 field sites, as you can see in this review. It was applied, it's already successfully applied in the source identification qualitatively, and the big advantage, quantitatively approach. For example, for vinyl chloride, for volatile chlorinated organic compounds, for BTAGs, for MTBE, ETBE, PAHs, heterocyclics, explosive pesticides. So many, many different compounds, many field sites. But the question is, what is about PFAS? So far, there is no CSI method available in literature describing a stable isotope analysis on PFAS compounds. That's why we focused in the last year on this development of such a method. Why so far there was no method available? It's because of you have certain of the methodology of the CSI, so how it's measured. Most important, it's measured, the traditional compound-specific stable isotopes are measured via gas chromatography, isotope ratio, mass spectrometry. That's why the first step is, for example, shown here by the P4, you need a GC suitable compound. So for separation of the compounds. So this is the first critical step. So you have to convert this, for example, P4 to GC suitable compound to be measured on the GC. After injection, those different compounds are separated by the gas chromatography, and then in the second step, they are converted to a measuring gas. In the case of carbon, it's CO2, so carbon dioxide. And of course, this is a critical step for isotope fractionation. And additional to this, there can also be some side product because of the fluorine, for example, hydrofluoric acid. So what really will damage your isotope ratio mass spectrometry. At the end, your CO2 molecules from each compound that are separated first are converted here, and then it's measured in the isotope ratio mass spectrometry by their mass. And as you can see, for the CO2, the most important mass 44 and 45, and the ratio between two masses are replacing your isotope ratio of your sample compound. So we developed now recently the first pioneering CSI method on P4. As you can see, we ordered, we buy just a P4 compound from the supplier, and we successfully measured isotope values in several injections with a high precision and a good accuracy and a high precision with an analytic area of plus minus 0.5 per mil. And not only this, we also measured P4 from a second supplier. And as you can see, we already were able to measure distinctive differences between those two P4 compounds, as you can see with the second one with minus 30.8 per mil. And that's why there will be some options for forensic investigations by compound-specific stable isotope analysis. Additionally, we also were able to measure shorter chain polyfluorinated carboxylic acid, as you can see. So we have first result that we can, those shorter chain carboxylic acid can be separated on the GC, and then also measure the isotope values of this. But the question was if also isotope fractionation, so a shift in the isotope ratio due to degradation, is taking place. That's why we applied two different chemical transformation reactions to apply at our CSI method. The first reaction was set up by my colleagues from the Helmholtz Center for Environmental Research, and it was reductive defluorination. Managed by hydrated electrons that were produced by the UV irradiation of sulfide, as you can see here. Then you have hydrated electrons, and further on, your fluorine atom is reduced from the compound, so we have a reductive defluorination reaction. So we took samples after certain times, and as you can see, with the further degradation of the P4, so on the x-axis residual P4 fraction, with the further degradation of the P4, we have a shift, we have a distinctive shift in the isotope value from about minus 30 to minus 10 per mil. So this was the first time that we were really able to show that isotope fractionation is happening during a transformation reaction. We are also able to calculate a proportional factor replacing or reflecting this isotope fractionation. It's an enrichment factor, as you can see here, for this distinctive transformation reaction. In addition to this, we also investigated a second example of chemical transformation. It was catalyzed by activated persulfate. It was heat activated, as you can see here, with a sulfate radical, and as you can see with further reaction with the sulfate radical, the P4 is further degraded, here carboxylated, as you can see in this chemical transformation reaction. And also we took samples after certain times, and as you can see, with further degradation of P4, we only see a minor shift, but still a significant shift in the isotope values from minus 30 to about minus 27 per mil. And also we were able to calculate here the prospective proportional factor. And in comparison of these two different chemical reactions, you see that we have two distinctive slopes, and we are already able to distinguish between those chemical reactions. So there are options really to calculate at the end, as for example, a success control, the percentage of degradation with this distinctive enrichment factor and independent from the concentrations. Additionally, and in summary, we were able to show that with the compound-specific stable isotope analysis on Pfas, there is the potential for differentiation of degradation pathways, as you can see here by these two examples. A quantification afterwards is possible of degradation, and also due to the measurements of two distinctive Pfas suppliers, we were able to do forensic investigations. So what is the outlook about this really nice, interesting topic, most promising topic? So of course, the first challenging step will be to go to the field site. Of course, there we have really low concentration of Pfas, as you already seen in the previous talks. So we have to do an enrichment of the Pfas out of groundwater or soil by, for example, solid phase extraction methods, and there we can also have some matrix effects. So we did some first experiments just really in the lab with water just before it was diluted, and then afterwards was extracted by SPE. We have really a good recovery, and we didn't see any isotope effects between this directly measured before and extracted after solid phase extraction. So there are options really to enrich the Pfas, the specific compounds from the groundwater. Secondly, and most important, of course, not only to stay on P4, of course, we have to broaden this method also to PFOS. We are currently developing a method not only for carbon, we also try to establish a compound-specific stable isotope analysis on the sulfur from the PFAS compounds. And of course, all the shorter chains ones, all the precursors, this is really high challenging to develop in the respective CSI method. At the end, our goal is really to establish a database on isotope fractionation factors for remediation measures that will be available to everybody and really can do degradation measures or remediation measures in the field sites and as a success control, or to evaluate maybe sources and sinks of PFAS contamination. I want to thank, of course, you for your attention. I want to thank to my colleagues from the Helmholtz Center Environmental Research. And this whole project's already started. And this year it's funded by the BMBF, the German government, and the so-called FATE-PFT is the title of a profound source identification and degradation evaluation of polyfluorinated surfactants in the water cycle by CSA as well as diagnostic ratios. And this project will end in 2023. So I'm also looking forward to present you more results later on. Thank you.
Thank you very much again for this really interesting presentation, and also presented in an excellent way. So double thank you. We will jump to the next presentation. Still 2 to go before we do the panel discussion. The next presentation will be about assessing and mitigating PFAS sampling bias, and it will be given by Jennifer Field. She has a PhD in geochemistry from Colorado School of Mines, and is working now at Oregon State University. I would say, Jennifer, the floor is yours.
Thank you very much. And I'm curious what display you're seeing. Is it shown in slide presenting mode or?
Well, it's with the next slide presenting mode, if you see what I mean. Yep.
Does
now
that
it's
help?
perfect. It's
all right,
helping.
Thank you so much. And thank you again for the opportunity to present this work before RenTech Europe. It's great to have so many new faces and names online. I would like to, I represent a project that is funded under the Strategic Environmental Restoration and Development Program based in the United States. CERDP receives its funding, as you can see in the upper left-hand logo, from DOD, EPA, and Department of Energy. And at least from the perspective here, it is aimed at trying to help solve problems in the DOD complex. And so I'd like to acknowledge my team members who are, I have the great pleasure to work with a number of consultants, Doran Bogdan, Rula D, Bill G. Giuseppe, Dina, Elizabeth, Dung, Charles, Trevor, and Amanda. These folks are coming from Jacobs, AECOM, and Geosyntec, as well as CDM Smith. And we're gathered trying to ask questions about whether bias occurs during sampling, because we are all engaged in sampling across the world, and we understand the need for a very high data quality. So I'll pass through our project team. It will be in the slides, of course. And then, so what's the motivation of this the study? So if you've been in PFAS for a while, or either a short time or a long time, for sure you've heard the concerns regarding PFAS being ubiquitous and commonly occurring in many, many things, among them laboratory materials as well as field sampling materials. Has certainly been a concern. The problem is we haven't had a lot of data to refute some of those ideas or to support some of those concerns. So the concern is if you have materials that are giving off PFAS, they may result in positive bias in your measured PFAS concentrations. The second one is we've heard also a lot of conversation about concerns about artifacts possibly resulting from storage and analysis due to processes that might occur, such as stratification within, say, a sample bottle, filtration, which is largely discouraged from aqueous samples, and the possibility of absorption to various different kinds of containers. There's so much discussion about what type of container, what kind of material. In terms of where our attention is now, there's really a really great body of work developing on the accumulation of PFAS at the air-water interface. You actually saw a presentation earlier about using foam fractionation as a way to exploit the air-water interfacial partitioning of PFAS. So it's a really exciting area, not only with practical applications, but also with a theoretical underpinning. And so when we start thinking about the air-water interface, clearly what comes to mind would be the possibility for enrichment in surface waters at that air-water interface, in groundwater at that small air-water interface in the well, sample bottles, even auto sampler vials for people who are doing direct aqueous injection. So why does this occur? Well, what we know from some really great work early on by Kai-Uwe Goss out of the EAVAG is that PFAS, those fluorinated chains, have very weak van der Waals forces, which is why they don't interact with anything, which themselves or oil. That's why they repel oil, they repel water, because those weak attractive forces are very minimal in PFAS. So in other words, they're very poorly accommodated in water. And so the water is essentially driving them up to the air-water interface where they can accumulate. And we now have ample evidence developing the literature that that is the case. The question is the degree to which it happens, and does it have an implication for sampling? And so we know that there's this potential for partitioning to interfaces. The question is whether it actually results in measurable bias. So the objectives of this particular project were to take a look at very real scenarios in terms of sampling, and to determine if there are factors that are occurring in the field in water columns, both surface water and groundwater, that might cause bias. And if this is the case, how to get around that, how to identify sampling approaches that might minimize bias. The second was to take a look at the field materials that we actually use when we go out and we sample for PFAS in the field. And this is actually published, and there's a little, I'll show you a link to that in just a moment. The third objective was to quantify the impact of sample hold times. Now, it turns out some great work has been done, and I'll actually point out some literature for those of you interested in this. So we actually didn't conduct original research on question or objective number 3. And the last one was to really take this information that we get from this project and from the literature to stakeholders, both federal, state, international, and contract labs where appropriate. And that's really to help inform the sampling guidance. So what we have is a combination of field and laboratory approaches. Stratification in surface water and groundwater has a field and lab component. The field sampling materials, that's clearly a lab study. We brought materials in. Sample storage, again, we deferred to that published piece. And then again, it culminates in outreach and technology transfer. And I'll point you to a document that is on the CERTIP website if you're interested in the culmination of this information. So just a few pieces out of this project. The big one that's already been out is the common field materials tested, simply because there was so much concern about the kinds of things that could possibly impact field measurements in, say, particularly water samples. So what we did is we went out and we either had donated or purchased 66 materials in commerce that are commonly used, and they kind of broke down along 4 lines. They're materials that you would actually use prior to arrival at a field site, pre-staging, actually used in the field, but not during active sampling, and then sampling itself, and then post-sampling, think ice coolers and chests and whatnot to ship materials around. So 4 different kind of activity-related batches of materials. All of these were extracted by methanol. It wasn't about water. It wasn't about partitioning in the water. It was really I'm trying to be exhaustive, in other words, to get the highest value you could possibly get, and then to take a look at those values. We analyzed for 50 target PFAS. This was done by liquid chromatography, tandem mass spectrometry. And because it's a methanol extraction, it is kind of a worst case scenario. It's more aggressive. We didn't use a reaction, but it's potentially more aggressive than just leaching. So think about these values, sort of worst case scenarios. So to give you an idea what's happened or what we actually looked at, if you look on the right at the pictures, we took some materials, again, there's 66, but here's some classic examples. In the upper right, we actually look at the ice packs. We had, I don't know, 5 or 6 different brands of ice packs. These are actually discouraged at the moment in several guidance documents, both at the state and federal level. There's been a lot of concern that ice packs, both their exterior and their interior contents, could be sources of PFAS. We found positive detections, but there's really no plausible path, for the ice packs, there's no detect. And that includes opening them up and analyzing the interior context. So no detection. Now, why would this be important? Ice packs are recyclable. They're green. You're not, using ice. You don't have the mess. So we've been avoiding something that really, at least to date, or at least in these 6 brands, doesn't pose a risk to your analytical data. In the case of aluminum foil, every now and then you use that in the field. We found one positive detection. It was actually on the box. It was stick resistant, or so that would suggest it was potentially treated. You get a positive detection, but what does this mean? If you look at the table at the bottom, we found a combination of PFAS and PFOA on a nanogram per centimeter squared. We got a value of 2.7. If you actually ask yourself, how much area of that foil would you have to have in a 1 liter bottle, and you'd have to release all of its PFAS and PFOA, would you need to reach the US EPA health advisory value of 70 nanograms per liter? I picked that number for just illustrative purposes. You need 26 centimeters squared. So I actually cut up 26 centimeters squared and put it in that bottle in the right-hand right-hand photo. That's how much material you'd have to stuff in the bottle and have all of that come out in order to reach that particular level. And so if you start thinking along those lines, like, could I really have aluminum foil impact my water if, of course, I don't do that with my aluminum foil? And I think what the data suggests is we need to start thinking about, when we have a material, whether it has a detection or not, we have to think about pathways, just like with human exposure. Is there really a pathway for the PFAS or PFOA on aluminum foil to get into your, say, water sample? If there is, well, don't use it. If there isn't, then maybe we don't have to worry about it. In the case of the ice packs, I'd have to put 6.7 of those ice packs to get to a theoretical 1/2 of my limited quantification. You can see that's not plausible. PTFE tape, I mean, we're quite aware that PTFE can have and does have residuals of PFASs in it, but you would need the quantity you see in that jar to get yourself to 70 nanograms per liter. So just a reminder, a hit doesn't necessarily mean that's going to translate to a hit in your water sample. So think critically about your materials, examine them, be skeptical, but also take a realistic view. In terms of equipment blanks, here's another case where people think that we have the potential, as we reuse equipment in a field site, whether it's a depth of water meter or a pump or lines. These are all very real and excellent questions. Do these materials have the potential to contaminate samples? So what happened is our great consultants actually went to their own databases with DoD-based data. So equipment blanks, this is a blank taking water through the equipment after having taken a sample. All these equipment blanks went into a giant database, and over a multi-year database, they had 279 positive hits for equipment blanks. 64 of those were above the LOD. Only 38 of those were greater than 1 nanogram per liter, and only 4 of them came from 2019 to 2020. We actually, from that analysis, we actually picked out a pressure transducer was on that list and had it tested, and it came back negative. And so the bottom line here is it appears that our current standards of equipment and practices in the field, we have very few equipment blanks actually hitting our equipment and databases. And that would suggest that current protocols in place are actually quite good in minimizing false positives in field data. So the key points are, please think about whether or not a field material or any material had direct contact between your sample. Most of the materials we use in field sampling do not. We still think, of course, it makes sense to avoid PTFE, and it's fairly easy to do and somewhat easily to recognize, like in the case of tape. But the risk is low, especially if the material doesn't come in direct contact, but we think it's generally a wise idea. And lastly, those sampling practices in terms of field sampling seem to be well established and developed for other contaminants, seem to be working well, as evidenced by what's in the DoD field equipment blank database. If you're interested in this information, there's an open access article listed below in ESNT letters, and we detail the equipment and the materials sampled and what we obtained. In terms of storage stability objective, I really encourage you to take a look at a fantastic study coming out of the Axis Lab in Canada. Wooden et al. Did a great job, and they performed a comprehensive storage stability study, and they basically found no systemic bias statistically, and they did enough replications, which makes it a great study, to conclude that they did not see bias in storage over glass, HDPE, or polypropylene over time. They looked at storage conditions, 20 degrees C, 4 degrees C, -20, up to 180 days, which is longer than what's currently in, say, EPA protocol. And they found it did not impact PFAS concentrations in a statistically significant way, except for the sulfonamidoacetic acids. So the sulfonamidoacetic acids are intermediates in the degradation of polyfluorinated sulfonamido-based compounds. And those actually in biologically active materials like wastewater and surface water did biotransform under refrigerated conditions. So if you're interested in those, if you're interested in sulfonamidoethanols, those are the ones to watch. Those are the ones to keep in mind when it comes to storage stability. Otherwise, these compounds, especially the legacy PFAS, the acids, carboxyl sulfonates, are very stable under the conditions that they examine. So please take a look at that. We moved on to looking at whether there's bias or stratification could possibly impact groundwater in standing wells. And so in a quarterly monitoring situation, wells stand quiet for about a quarter. Now, of course, quiet in the sense that nobody's in there sampling, but of course we have groundwater tables moving. We have, they're not totally static system, but they're left undisturbed for a quarter. So we were interested to know in low salinity and high salinity conditions. And if we sampled at low, medium, high in these model groundwater wells, they're not terribly large, they're what, a couple meters high, can we see any evidence of measurable differences in PFAS concentrations as a function of position in this water column? The punchline is, the answer is no. Within low salinity and high salinity wells, so that we had triplicate freshwater on the left, one DI control in the middle, and there was no background. And we had one high salinity, same groundwater, just taken to higher salinity. When you measure those top, middle, and low ports, you see no statistical difference between those measured concentrations. We concluded, now that doesn't mean that stratification is not occurring. It's just that interfacial area is likely very small, and the impact of that area for that water column is very small. So we conclude there's really no need to modify current groundwater monitoring programs because, for example, if you're going to drop your pump through this water column, you're going to have further mixing. If you do low flow, it's designed not to capture the upper portions of the well water anyway. And so if we actually took this measure data and compared it to theoretical predictions, and that's where this great literature is coming from. KI, the air-water interface, there are values for that in the literature. You can actually take the interfacial area of the monitoring well, and we calculated the mass that we would expect at that interfacial area. And if you look at the bottom here, the fraction of PFAS, you would expect that interface is only 0.33%, and that's obviously within our analytical error. In higher salinity, you might expect more PFAS at the interface due to the salting out effect, up to 2%, still within our uncertainty of analytical. So the punchline is we don't think that's very much an issue. In terms of moving on, the surface microlayer, some really attention focused on it.
Jennifer, sorry to interrupt you, but could you come to a conclusion?
You bet. So the punchline is that if you have foam, and you're in an area where it's naturally foaming, as we have seen in our upper states, the punchline on stratification is you need to avoid foam when sampling surface water because elevated levels of PFAS do exist with foam. That's why you saw the talk earlier on foam remediation, because foam is a very effective means by which to collect PFAS out of water columns. But when it comes to the surface microlayer in the absence of foam, though the concentrations in the microlayer are 4 to 10 times higher, not 4,000 times higher, which we have seen in the case of foam. So we're currently in the process of determining if the technique by which you sample surface water can actually impact measure values when in the absence of foam. And the last thing I want to bring your attention to is we have a report on the CERTIP website that puts all of our current knowledge of sampling guidance together in one location. And we'd be pleased if you visited that site and took a look at the report. Thank you very much.
Thank you for this excellent and very interesting presentation. And I now hand over to Stephanie.
Yes, thank you. Okay, so our last presentation of this session is from Dr. Hunter Anderson. He joins us from the U.S. Air Force Civil Engineering Center in San Antonio, Texas, where he provides technical expertise to AFCEC's environmental restoration program in the areas of emerging contaminants, environmental engineering, environmental toxicology, and quantitative data analysis. He also represents AFCEC to the U.S. Defense Department's Strategic Environmental Research and Development Program. And with that, I'd like to turn it over to Dr. Anderson and remind everyone to ask questions in the chat for our upcoming question and answer session. Thank you.
All right, well, yeah, last but not least, Stephanie, I'll just confirm everything's working right. Looks good.
Yes, it does.
Okay, yeah, thanks. Well, yeah, greetings from Remtech Europe, along with several presenters today. Greetings from across the pond, in my case, San Antonio, Texas. This talk, unlike most of the talks today, is not going to be focused on a particular remediation technology or case study, but rather how one would establish a decision logic in order to determine the need for undertaking a remedial action specific to what I'll define as a source zone, and I'll describe that momentarily. If you're an entity that only has 1 or 2 of these impacted sites, maybe it's not worth studying. Maybe you just jump to the end, be proactive, conservative, treat everything as well as aggressively as you can treat it. But the United States Air Force is the biggest Air Force in the world. It stands to reason that we got one of the biggest AFFF liabilities in the world. And so we have, literally thousands of these impacted sites. And so we have to be tactical in terms of how we think about undertaking these remedial actions. There's absolutely billions of dollars at stake here. And so this is, some of the logic that we've incorporated into our programmatic practice in terms of how we do that. And I should note that while I work for the Air Force, I'm sort of representing DoD at large here. Jennifer just described the CERTIP, and there's a sister program, ESTCP, where we're heavily involved in terms of soliciting this work from the smart people like you've heard present today, Jennifer included, that develop the data and rationale for how we do things in practice. And so because of our extensive portfolio on this topic, I sort of am representing the DoD at large here. Okay, so moving on, everybody's probably seen the PFAS cycle. You're well aware of how these chemicals sort of migrate and behave in the environment. Much of the focus, today and elsewhere is on drinking water, and rightfully so. That's driven largely by the relatively low and ever, increasingly more conservative drinking water criteria that's out there in the world. But if you really look at the case studies that have developed the mass budgets for where all these compounds reside in these impacted sites, it's overwhelmingly obvious that, that 90 plus, if not 99+% of the mass resides in the unsaturated vadosome soils, whether they be from emissions, manufacturing emissions type sites or AFFF impacted sites. And of course, the deeper that vadosome gets, the more prolific that mass budget becomes in the unsaturated zone. And so I'm glad to see some interest here and some evolving effort related to the treatment of unsaturated soils. But again, before one decides to do that, we've got to understand if and when the decision to remediate those soils is actually going to make a difference. These are just a bunch of our data from our portfolio at this point. We're nowhere near the end of our characterization efforts, but we have data from thousands and thousands and thousands of boreholes, hundreds and hundreds and hundreds of sites. And this is just a statistically integrated example of what the average sort of profile looks like as a function of depth. You clearly see an exponential decline in concentrations with depth, as well as a fractionation effect, where the short chain compounds begin to dominate the total concentration, albeit a lower total concentration. That fraction is increasingly represented by these short chain compounds with that, reflecting their greater mobility in the subsurface. And another way of looking at all that is to just compare boreholes where we collect soil samples and the co-located groundwater samples across the entire portfolio. Again, thousands and thousands of samples. We clearly see greater concentrations in soil relative to groundwater, all else equal, and that divergence increases as the chain length of the compounds increase. But it's not linear, and you know, it tends to be this bimodal sort of effect where the short chain compounds exhibit one behavior and the longer chain compounds exhibit another behavior. And so the transport is rather complicated, as I'll get into, but this is all published. You don't have to take my word for it. These documents here include all the data just presented along with a thorough description of how they were generated and analyzed. So given that these Beto zones represent, you know, the predominance or the preponderance of mass at these sites, it stands to reason that how we think about their source strength, as we call it, is in terms of flux. So the spatially integrated mass within the footprint of these impacted soils as they traverse a cross-sectional plane that's parallel to groundwater above the water table. That cumulative amount of mass per unit time is defined as the mass discharge, and that's our metric of source strength. And that cross-sectional plane at depth shouldn't deviate significantly from the footprint at the surface, and that's largely because the vast majority of these compounds that we're concerned about are non-volatile, and so there's not significant dispersion through the soil gas matrix that manipulates the footprint at depth relative to the surface. And so we can delineate these surface soils to the extent that these sites aren't disturbed, and get a sense for what the footprint looks like with depth, characterize the vertical profile, and then collect data that's necessary to generate these mass discharge estimates. And that's what I'll get into. But conceptually, it's really simple. What is the mass discharge from soil to groundwater compared to the mass discharge from groundwater plane A to groundwater plane B? And that defines whether or not the surface soil contamination is or is not problematic in terms of sustaining a groundwater plume above criteria or not. And that's sort of step one in our regulatory process in the United States under SORCLA. We have to make that decision and justify why we're spending taxpayer dollars to do things like soil washing, thermal desorption, isotope fractionation, forensic analysis, all those things you've heard about plus more in order to justify, you know, our use of those dollars. But before we talk about exactly the methods by which one goes about to do that, I think it's important to just highlight some of the salient conclusions that have emerged in the literature thus far in terms of absorption. So why are these source zone soils 20, 30, 40 years after the cessation of AFFF use still represent 99+% of the mass at these sites? And that has a lot to do with their solid phase absorption. Yes, as Jennifer indicated, the van der Waals forces aren't as significant as a lot of other contaminants, but these compounds, as ionized organics, do interact with soil organic matter. It's not quite as straightforward as just the traditional KOC-FOC approach. We know the pore size distribution matters. We know the surface area matters. We know the composition of the organic matter matters, but also what's typically neglected when we talk about solid phase absorption of PFAS, especially the ionized PFAS. Some are neutral, but the vast majority are either cationic, zwitterionic, or anionic. There's an electrostatic interaction with most soils. All soils are charged. They're either negatively charged or positively charged. The vast majority are negatively charged, at least in the northern hemisphere of the world. But so certainly cations interact electrostatically to a greater degree than anions, at least in most soils. But even anions can interact with certain soils appreciably, and that has to do with the variable charge clay minerals that can exhibit an anion exchange capacity. But moreover, there tends to be this intersphere complex capacity with soils that are rich in iron oxides that react with things like oxyanions, like sulfate, for example. So it shouldn't be a surprise that some of those same reactions apply to things like PFAS as well. And I think there's a growing body of evidence in the literature that suggests some of these electrostatic interactions with PFAS in particular are in fact potentially covalent, but at a minimum operationally defined as irreversible. And so what goes onto the soil isn't necessarily what comes off. And you heard Jennifer describe how exhaustive it is to get some PFAS off of some soils with methanol, But regardless, if you can do that, that's not necessarily representative of what would come off under ambient in situ conditions with soil solution. And so the point is, solid phase sorption of PFAS matters. It's more complicated than KOC, FOC, and the electrostatic interactions are highly relevant, but often discarded or ignored. But as you've heard extensively at this point, this air-water interfacial behavior is highly relevant for PFAS. These are surface active compounds. They partition across these air-water interfaces. And unlike bubbles in the case of SAF and in a downhole monitoring well, soil solution occurs in an unsaturated soil as a film across the solid phase, and that creates an air-water interfacial area. And it's that air-water interfacial area where these PFAS ultimately partition. And people have done these really elegant experiments with unsaturated soils where they've incontrovertibly demonstrated greater retardation under unsaturated flow. And that has to do with this accumulation at air-water interfaces. So at any time in a porous medium, when there's air exposed to these molecules, that results in what's referred to in the literature as a surface excess. And that surface excess retards transport. So in addition to the retardation that occurs due to the solid phase sorption, there is this retardation that occurs due to air-water interfacial accumulation. And I'll just make a point for the record that as a card-carrying soil scientist, I'm obligated to tell you that the amount of air-water interfacial area in an undisturbed in situ soil profile, all else equal, is much, much, much different than what occurs in, say, a packed column or a packed bed. So when you do these experiments or you take soil samples and you manipulate that material and you process them in a way that you destroy the structure that's inherent in an undisturbed in situ soil sample, you greatly manipulate that air-water interfacial area such that the transport that's observed isn't necessarily representative of the in situ conditions, and I would argue represents a worst case scenario. So this is why it's important to do things either in situ or with undisturbed soil samples, as was in the case with what Stephen presented earlier this morning. And so I was glad to see he did that. Another example for why retention in soils is relevant is the fact that there's this salinity effect. In general, as salinity increases, you increase the fraction that sorbs to both the solid phase and the air-water interface, at least within the environmentally relevant range. And it's referred to as the salting out effect. And it has to do with the boundary layer thickness for these electrostatic interactions. As things get saltier, they sorb more. And that's relevant to soils because soil solution tends to be quite a bit saltier than the corresponding groundwater at a given site. And that just has to do with all the biological processes within the rhizosphere. Again, emphasizing sorption within unsaturated soils relative to, say, aquifer solids. But one of the more complicating factors to all of this is the kinetics. So there's a lot of the sorption that occurs essentially instantaneously. That's with the air-water interface. But especially with organic matter, because of the pore size distribution effect, there tends to be this highly rate-limited kinetic component to all of these sorption processes with the solid phase. And there's a preponderance of laboratory and field data that's out there that demonstrate this. Highlighted on the slide here are just a couple examples. But to suffice it to say that you cannot assume equilibrium conditions under an in situ scenario. There is a rate-limited component that greatly produces artifacts in terms of what would otherwise be a prediction based on laboratory measurements. And so all that's led to the development of these conceptual models that are in the literature. There's a solid phase sorption component. There's an air-water interfacial sorption component. There's a rate-limiting component. There's an equilibrium component. And then due to the structure of in situ soils and the pore size distribution effect of organic matter, there's this advective component where water kind of rapidly transports through soils and the organic matter matrix, and this non-advective water domain where solutes move by diffusive fluxes through the interstitial component of the matrix within the structure of soils. And so it's this sort of 8-parameter problem that people have deduced that would be necessary to parameterize in any kind of predictive capacity. I'll come back to this in a moment. But all that stands to reason, if the conceptual model is that complicated, then, okay, so how does one go about utilizing all this information in practice in terms of making decisions about whether a source zone is or is not problematic? And sort of the first and most obvious methodology has been presented earlier today is this batch extraction. And different jurisdictions, different countries have different deviations on this, but Nevertheless, they all involve the collection of a soil, the processing of that soil, air drive sieve, aliquot, some sort of saturating extraction fluid, whether it be water, buffered salt solution, what have you, and then aggressive agitation, some sort of separation, and then a measurement of that aqueous phase. The problems with this is it saturates the sample, so you've eliminated all air-water interfacial retention that would otherwise occur in situ, and you've aggressively agitated the soil such that you've solubilized any water unstable colloids or aggregates. And not all of those colloids and aggregates would then get separated out. People rarely use filters for these type of analyses. And so you get this additional mass phase in the aqueous matrix that's analyzed along with the aqueous phase. And so as a representation of the actual pore water chemistry, I'd say this particular methodology is fraught with issues. As a relative methodology to compare pre and post remediated soils, however, I think it's perfectly relevant, but I think it's important to keep in mind the limitations of some of these methodologies. And in terms of being a representative surrogate for the actual pore water chemistry, I would say a batch extraction doesn't do a very good job. Of course, there's column experiments, and we can get into all that, but for the sake of time, I'm going to jump straight to the meat of all this. And I would say, for the sake of argument, it's a lot easier, a lot more straightforward, a lot less uncertain to simply sample the pore water. As you've already seen presented today, lysimeters are common practice. They've been around for decades. People have been sticking lysimeters in cornfields to measure atrazine since the 90s. This is a very standard industry practice. And there's a lot of different caveats in terms of what lysimeters to use, how to use them, what lysimeters apply and what sites and where. I won't get into all that. I'll just say that we have SOPs for all of them. They're commercially available. There's a tremendous number of vendors that can supply these things. They're out there. So if you can obtain a pore water sample with a lysimeter, however it's collected, the options are, like I said earlier, to compare the mass discharge, to spatially integrate those pore water estimates using some sort of geostatistical approach into a mass discharge estimate from soil to groundwater, and then compare that estimate to similarly derived estimates within a groundwater plume with increasing distance from the source. And then you get a relative sense for where all the mobile mass is. And if the mobile mass is moving from plane A to plane B in the groundwater relative to the soil to the groundwater, I would argue you don't have a soil problem on your hands, and you should prioritize your remedial efforts on the actual groundwater plume. Conversely, if the majority of that mobile mass is still leaching to the water table versus advecting down gradient from the source, then you've got a soil problem on your hands, and you should prioritize remediation of soils. And for all of you thinking that this is so infinitely complicated, it could never be done, well, there's a published case study that's been recently published in the Remediation Journal. This was done jointly by the Arcadis team and the PACE Analytical Lab team with CERT funding, with the use of an application of a mobile lab to generate data essentially in real time. I won't get into the details, but there's a very elegant case study where this type of thing has been demonstrated. Alternatively, you can, and we can get into the strategy and where and how many lysimeters to use, but you can generate a site-specific pore water project action level based on basically a default attenuation factor, or a dilution attenuation factor from soil to groundwater. And you can think of this as sort of analogous to how people compare soil gas measurements of VOCs to indoor air criteria or vapor intrusion pathway. There's always some sort of dilution attenuation factor that's applied to convert a soil gas measurement to an indoor air measurement. Likewise, you can convert a pore water measurement to a corresponding aquifer sample, groundwater sample measurement through a series of parameters that would ideally be defined in any comprehensive site investigation. But ultimately, where all this is going is, as the research develops and the people that are doing all this work, we want to have the capability to take these lysimeter-derived pore water measurements, plug them into a comprehensive vadosome model, and then make predictions about how things behave and what needs to be remediated and what will happen to the water table if that remediation occurs. We've been doing this for a while. I've noticed a bit of a learning curve with our contractor community. It's a bit involved. I mean, you do have to do some prep work, but it's nothing that's not straightforward. There's SOPs on all this, but the materials have to be cleaned. We have done all the equipment blanks. They're absolutely PFAS free. They can be installed with conventional borehole equipment. A 4-inch borehole is all you need. You pack the porous portion of the lysimeter with a material called a silica gel, and then you seal the hole with bentonite, and you backfill with native material. You sacrifice the first sample to eliminate the dilution artifacts. And from there on, assuming there's adequate soil moisture to sample, you get a sample as often as you need. You can finish the lysimeters flush mounted or in a vault, just like a monitoring well. And if I haven't convinced you thus far, there's a very thorough description of the logic behind all this and the information I've just presented that we recently published in the EST. I recently published in EST. And with that, I'll hand it back over and we can hopefully start a good discussion on all this. So thank you very much for your attention, and I'll stop sharing my screen.
Oh, great. Great presentation, Hunter. And so I encourage people to contribute to the chat. I'm going to go back to one of the first questions we received, and this one is for Anna. And the question is, maybe I missed, but what is this situation of contamination in groundwater? I saw remedial actions for soil and surface water, but no contamination nor risk for groundwater.
Yeah. Actually no action was taken on groundwater. PFAS were detected, but since the aquifer was a perched aquifer was a seasonal aquifer, only during winter water could be collected from monitoring wells, and there was no usage of water at the site, nor a potential risk of PFAS migration from the site because of the low productivity of the aquifer in the silty matrix. Based on the risk assessment, it was deemed not necessary to do any action for groundwater.
Okay, thank you, Anna. The next question that I have is for Helena. Now, you answered in the chat, but in case people missed it, I thought I would go ahead and ask you so that you could discuss it here, which is the question was the efficiency on PFBA and PFBS. And if you could just describe again, as you did, what you might do for that approval of efficiency. If you're answering, Helena, you're on mute. If not, there was also a question to Stefan, which is which you did answer in the chat, but I would ask it again just to be sure everyone knows the answer. There was a question on the relationship between soil moisture and rendement, and what other parameters might be influencing the rendement.
Yes, good question indeed. As I already answered, one very important aspect is the soil composition, especially the fine structures of the soil, because it influences greatly the PFAS sorption as well as the sorption of the biopolymers. We can influence that to some extent by changing slightly the pH, but apart from that, yeah, this is probably one of the most important aspects.
Okay, I had a question. I know towards the end of your presentation, you had a slide that showed the treatment of a number of different PFAS, but it went by pretty quickly, and I couldn't see how the treatment of some of the short chain compared to the long chain. Could you discuss that, please?
Sure. Yeah, the short chain and long chain PFAS could be eluted quite efficiently. We had much more difficulties with the desum pub, the sum pubs and the desum pubs, and the precursors were turned out to be much stickier, and then you would not find the precursors in the aquifer itself. So obviously they are extremely sticky in the topsoil.
Okay. All right. The next question is for Kevin Kunze. And this one was about, could you foam the low PFAS concentration liquid to enrich the liquid and then run the same CSIA process for forensic purposes?
Yeah, for sure. This would definitely be an option to enrich the PFAS directly from the field side or from the groundwater. So, but it depends on, you know, not just as I showed, we established a method for P4 or some shorter chain carboxylic acid. So the question is, what else will be measured then via CSIA? So we have to check really matrix effects. We have to check if we have a good separation. So that's why this is the high challenge, really, to go to the field side and really direct. But for sure, I already chat with Rebecca. There will be option, and this is why we're running this R&D project to really check if this is possible.
Okay. Let me continue on. Okay, there was some also some conversation about your proposition on PFOS.
Yes, I think Hunter questions. He doubted that we had no isotope fractionation with PFOS. We have to check. We have to first to develop a method for PFOS. The challenge is to make them GC suitable, to that we can measure those on via gas chromatography coupled to IRMS. But nevertheless, we showed it by P4 that with hydrated electrons, we have a reductive defluorination. Therefore, also other people had doubts before that we do see isotope fractionation. By the end, we did see, and we did significantly isotope fractionation. So the rate limiting step is really first a bond cleavage of the carbon and the fluorine atom.
This is Jennifer. Can I ask Kevin a follow-up question?
Yeah.
Sure.
So Kevin, you didn't have enough time to give a lot of detail, so I appreciate that fact. So you injected a PFOA standard onto a GC-MS, or sorry, not MS, but a GC isotope mass spectrometer?
Yeah, so this was just a pure P4 compound, yeah. So
yeah, so there is a growing literature that, I mean, I think we all recognize it's not inherently volatile. It's volatile maybe perhaps in the free acid form only, but that upon injection, there's thermal degradation of the carboxylic acids. At least to one group is known as superfluoroalkenes. So when you talk about studying degradation and reaction, I'm a little concerned that just the injection itself, that you're not really measuring PFOA. There is some discussion in the literature about that. I put the reference in the chat box. So I think right out of the gate, you may be measuring a reaction product and not the PFOA itself. So I don't know, I'm not an isotope person. I don't know if that's going to have an impact or not. It's just, I would take a look at that literature.
Sure, I will take a look, but the P4 is derivatized. So it's a,
oh, you derivatized, okay.
Yeah, it's a methylated, and that's why it's stabilized in the GC, and that's why we can measure this over GC RMS.
Yeah, that's how we measured PFOA the first time back in, a long time ago. And it's one of the only compounds you can't derivatize the sulfonates. People have tried.
Yeah.
It's a very good leaving group. So but there is this growing body of reactions under thermal conditions that includes GC ports. So I just wanted to make sure that that's on your radar screen.
Yeah, it is. But yeah, as is right.
Yeah, this is Hunter. So I guess I was thinking about the application of how you would use all this. And I guess in terms of a line of evidence to support a destructive laboratory-based technology experiment where you're trying to conduct mass balance, or account for the mass balances would be great. But in terms of any kind of like forensic application, as you alluded to, for PFAS, it would be rather one-dimensional because the only process by which PFAS degrades is this hydrated electron. And so you wouldn't be able to discriminate different processes. It would just be a yes or no, it's degrading or not. And I think on a field site, all you got to do is watch PFAS go away and fluoride go up. But
yeah, but still, you have the success control of this degradation processes, so of this remediation measures you're doing. So And additionally, we're also trying to set up isotope analysis on the sulfur. So maybe then we have a second element to measure, so we can have a two-dimensional isotope analysis, which will really enlarge the application also, especially in the forensic study, because then we are only snapping all the sulfur-containing PFAS. So this will be also really an option. It is challenging, I know, but it's really, I think the first results are really promising. It's the first method that hopefully will be soon published on this.
Kevin, how many sources of PFOS would you expect in a European setting where AFFF is used? And here, it's pretty much just 3M. I'm curious if you have multiple PFOS sources.
Oh, for the field, I cannot answer. So far, I have to check. So first, we stayed, let's say, on in the lab, and now we are applying more to and checking out the field sites.
Yeah, because I think it would be tracking 3M's signature, isotope signature over time to see if it actually changed or not. But like there are no other real big sources of PFAS. So that like PFAS is not the big unknown in terms of where it comes from or who made it from an isotope point of view. There's other stuff that I think is more like for me, the big question is whose PFOA is it? Because it's not clear because it can arrive either from ECF or fluorotelmer. I think that's the big mystery that maybe could be solved with isotopes.
Yeah, and also I think additionally also the transformation reactions from precursors maybe to PFOA. This is also interesting. So this has to also be conducted maybe in the lab. Maybe we did see also there a special isotope fractionation. So in comparison to the transformation order when it's produced. So this is really, I think there's a high potential for this also.
In Europe, we have a few producers, so not only 3M, we have a few others as well.
Yeah.
But I suspect those others probably still use the same electrochemical fluorination method. I mean, it's not like solvents where every company has a proprietary manufacturing process. I mean, there's two chemistries and that's it. And you know, so I would just encourage you, to focus on PFOA and, the carboxylates, because that's where the bang for the buck is, precursor transformation, that's where it all occurs. There's different sources, it all blends. We don't know who's whose, but PFAS is there and it doesn't go anywhere.
Okay.
It's not as a thing.
Okay, thanks for this advertisement.
Yeah, the precursors that would transform to PFOA would largely also produce only linear PFOA. So I would put that in your toolbox together with your isotopes. It should all hold together.
Yeah.
Because fluorotelmers are the most degradable, but yet they're also linear.
Okay, I have a question for Hunter that's come in. Hunter, the question is, what do you think about passive sampling of PFAS to determine flux? And what are the challenges that you think this poses?
Yeah, so I mean, assuming that you've got I just tried to turn my camera. Assuming you've got a sampler that, readily equilibrates, or else you understand the kinetics really well, I don't care, how the sample's obtained. It's essentially a surrogate for the pore water chemistry. I mean, you're integrating the pore water concentrations over time, which does the same thing. And as long as all that is representative and it's a defensible thing that has been validated, and again, SERP's heavily invested in this technology. We're looking at a number of different sorbent materials to use as passive samplers. But absolutely, to the extent those can be located in soils, it's a little more difficult, to do that relative to just hanging them in a groundwater monitoring well. But if somebody can figure out how to do that, I certainly wouldn't be critical of it. Sure.
Okay. All right. I have a question for Jennifer. When you were doing your study of, sampling materials, sampling stratification, all the three different aspects that you examined, were there any findings that surprised you?
Ooh, that's a good question. I think the thing that's really pretty interesting is that the foam is so highly concentrated, yet I have to say it's consistent with what we know about the aerosol literature coming out of Stockholm. There's some great work there, the foam fractionation. I think those elevated concentration and in a natural setting, not at we have the engineered setting in the natural, but the surface microlayer does not have as high value. And that makes sense if you think about foam as a three-dimensional structure with a large surface area, Whereas a two-dimensional, I think what we're seeing is in these cartoons of surface microlayer, there is these lovely cartoons coming out of the oceanographic literature that suggest three-dimensional. It's a three-dimensional, very thin layer. But I think here our data suggests that the PFASs are in the two-dimensional surface of that possibly three-dimensional layer. So I think moving from surface microlayer to foam is interesting. I think what we'll see is that the surface microlayer in the absence of foam will not cause a significant difference in the measured values when you use different techniques, but hopefully the data will support that. So big surprises, no. I think the one thing I think it surprises people that we didn't find contamination everywhere, but seeing the real data really got us thinking about pathways and routes of exposure. So it changed how we also started to look at our materials. And I think a lot of the issues that we have really simply are in the lab. They're from, and everybody who does analysis is not surprised by this. It's a constant daily, we're always monitoring salts, solvents, materials, lots, everything. I think most of the artifacts come from the lab environment, but everybody's doing everything they can to monitor for that and prevent that. But most signatures don't seem to be coming from field-related activities.
Okay, if I could just follow up quickly with your discussion of the foam and the surface microlayer. Are you aware of work that's looked at like collapsed foams? So like there was a foam structure, perhaps, like a superficial, AFFF that did collapse over time. Does that become a homogeneous concentration within the surface or within the water body? And how quickly does that happen?
Wow, that's a great question. We have not studied AFFF per se. The foams that we've dealt with are naturally occurring. And what's really fascinating is they are forming and breaking on very short timescales. So you'll see foam, you'll see foam, you'll see foam, and the next day it's not there. So it's very much a function of conditions. And when that foam relaxes back, it becomes a surface microlayer, but doesn't keep that intense concentration because the surface area presumably is low now at that point. Analyze AFFFs off the time, but we don't foam them because they're very difficult to handle. Like a foam that inherently doesn't infiltrate. It must collapse first before infiltrating.
Okay.
So it's been a wild ride trying to deal with foams and microlayers. It's been very interesting and logistically to handle them.
Okay. All right. Well, I need to tell everybody that we are officially at the end of our time. I know it's much later elsewhere in the world than it is here in United States Central Time. So you all are welcome to go, and continue on your day. I want to thank all our speakers who really had excellent presentations in this super interesting session. I want to thank my co-chairs. I want to thank RemTech Europe for putting on such a wonderful session. And Marco has been putting information in the chat about how to, access information later and get your certificates of attendance. So be sure to check that if you're interested. And I'd like to let Wouter and Edith, if they have anything they want to say at the end, or Marco, join in before everybody leaves.
Yes, I would like to thank you, Stephanie, Edith, and Wouter for chairing this session. It was one of the more crowded that we had in RemTech Europe because, PFAS is a topic at the center of the discussion also here in Europe, not only, also in America and Australia and wherever in the world. So I would thank you also to all the speakers and to all the people that still 75 are still present now, and that is late in European time.